today we're going to be doing surds. So what is surds? A surd is an irrational number. Like the square root of 2, that is irrational. We do not actually know what the real value of the square root of 2 is. It goes to infinity. The square root of 3, the square root of 5, the square root of 7, the square root of 10, square root of 11. All of those are irrational numbers. They're not perfect square numbers at all. Right? But notice, it's the square root, and inside the square root we do have a rational number in there, right? So it is an irrational number. That is the root of a rational number, the root of a rational number, and it gives us an irrational number. That is a surd. Yeah, so a surd, because this is irrational, means that expressing it in this form here, this is the most exact form of the number. Right? There is no more exact form than this to express it in. If you're expressing it in decimals, you'll have to round off. Wouldn't be exact. So this is the most exact way we could express it. And of course, a surd of the second order involves a square root. So of course, the third order will involve a cube root. Right? The rules that we're gonna learn today kind of goes across the board, but most of the time you'll be asked square root questions. These questions come very, very small, and in between, in a little paper one, you might get a couple of questions on surds, right? So it's not a big topic at all. Logarithms is one, though, that comes every paper too. Right? So you can see we have some rules about surds here, right? Like if I have the square root of a times b, for example, that is the same as the square root of a times the square root of b. Right? So if I was to have an example here being the square root of 9 times 3, that is the same as saying the square root of 9 times the square root of 3. Right? Or if I have, for this second example here, the square root of 2 on 5, that is the same as saying the square root of 2 over the square root of 5. So these are little rules that we need to already kind of know, and we're gonna add to those rules today. So you have a little example here where we have the square root of 75. The square root of 75 could be seen as the square root of 25 times 3, that is 75. And of course we could split that up into the square root of 25 times the square root of 3, which is 5 root 3. So you see, the part that is not a surd, the part that could be reduced to a rational number, we will reduce it. But this part here that cannot be reduced to a rational number, we leave it as a surd, right? So this here is the simplest form of a second order surd. That is when you have a constant and the surd with it. The reverse is also true. So if I have 5 times the square root of 3, I could put a square root sign over here. So 5 is really the square root of 5 squared. That is 5. Yeah. So the square root of 5 squared times the square root of 3, which is the square root of 25, times the square root of 3, which is the square root of 25 times 3, which is the square root of 75. So we could also do it the other way as well. Just recall these little rules that you're supposed to know already. For when you have even roots, even being like a square root, or a fourth root, or a sixth root, for any even roots, you'll have plus or minus the square root of a squared. And of course, plus or minus the square root of a squared will give you a minus a or a plus a answer. For example, the square root of 25, we know could either be plus 5 or minus 5. We know this, and we've seen it in quadratics. When it comes to even roots, you cannot have the square root of a negative number. The square root of a negative number does not exist, is what this symbol means. So we cannot have the square root of 25. That does not exist. It's not even undefined. It literally doesn't exist. For when we have the odd roots, however, we can have like the cube root of a cubed, and that'll be plus a. And then the cube root of minus a cubed will be minus a. So I could have the cube root of 125, and that will be plus 5. Or I could have the cube root of minus 125, and that will be minus 5. So for odd roots, you can have a negative inside of the square root sign. Now let's talk about when we are adding and subtracting surds here. And I do have 2 examples that you see in here. So example A, if I have 2 root 5 plus 7 root 5 plus 4 root 5, well, you could treat root 5 like x. So it's kind of like 2x plus 7x plus 4x. You just add the 2, the 4, and the 7 because it's all the same number, right? So you'll just get 13 root 5. So you could treat if it's the same surd, you could treat it like an x. So that is the first one. The second one, if I have the square root of 27 plus the square root of 108 plus the square root of 48, I have to now try to split these numbers up so that they have a common surd. So what could be the common surd? Well, 27 could be seen as 9 trees, 108 could be seen as 9 times 12, and 48 could be seen as 8 times 6. No common surds yet. I noticed though that the only actual surd is this root 3, right? 12 could still be split up, and 6 could still be split up. So I have my 9 times 3 here, and I split up the 12 into 4 times 3, and I split up the 6 into 2 times 3. So now look, I have a common surd here, and everything else, this 4, and even this 8 times 2, 8 and 2 are surds by themselves. They are irrational by themselves. But if I do 8 2s are 16, well, that is a square number, right? So I could find the square root of that. So I could combine the 8 and the 2. And so you could see here that I ended up with 3 being my only common surd. So now I could split it up into root 9 root 3 plus root 9 root 4 root 3 plus root 16 root 3, because this is really 16 times 3. I can see root 9 is really 3 root 3. Root 9 is 3 and root 4 is 2, so that's 3 times 2 times root 3. And then the root of 16 is 4, that is 4 root 3. And so now I can see that's 3 root 3 plus 6 root 3 plus 4 root 3. And so the final answer is 13 root 3. We have 3 questions here. How about we just try one for now and we'll leave the other 2 for homework. Let's try part C. So try part C and tell me what you get. So the first thing I noticed is that 45 was 9 times 5. And so I had this surd here with the root of 5. So I tried to see if I could find the root of 5 in the others. And yes, I did. Because 80 is 16 times 5. And then 125 is 25 times 5. And of course here, 25, 16, and 9 can all be reduced in terms of the square root. Right? So those are not surds. And so we have root 25 times root 5, root 16 times root 5, root 9 times root 5, which gives us 5 root 5, 4 root 5, 3 root 5, and that adds up to 12 root 5. the multiplication of surds. And this, we are reminded of a couple of things. So remind ourselves of a difference of two squares. Like if I have a squared minus b squared, well, that is just the square root of a squared, which is a, plus the square root of b squared, which is b, into the square root of a squared, which is a, minus b. This is the difference of two squares. If you expand this out, you'll get back this. Similarly, if I had the square root of a plus the square root of b into the square root of a minus the square root of b, if I multiply this out, so root a times root a will give me root a squared, right? Root a times minus b will give us minus root a root b. Root b times root a will give us plus root a root b. And root b times minus root b will give us, this is supposed to be a minus here, minus root b squared. And so you'll see here that this will cancel with this, and so we'll end up get root a squared minus root b squared, which ends up just giving us a minus b. It's pretty much the same principle. So this means that if I had the root a plus the root b, and I multiply that by the root a minus the root b, we will remove the surds. So this is our way that we use to remove the surds. Remember, surds are irrational numbers. We actually don't like them very much. So because when I multiply one you could say is the opposite of the other, and when I multiply them together, the surds cancel out, right? We call this the conjugate. So root a plus root b is the conjugate of root a minus root b. So this conjugate form is what we will use to do something called rationalizing. Recall just a couple of things before we actually get into it. If I have a plus or minus b squared, what this really means is that I have this multiplied by itself. That is what that really means. And so a times a will give me a squared. A times b will give me ab. B times a will give me ab. That's how I end up with 2ab in the middle. And then b times b will give me plus b squared. Even if it's minus, both of them is minus, you'll end up get a plus. So when you multiply this out, that is essentially the form that you get. You should be familiar with it from quadratics or used to this. Similarly, if you had the root of a plus or minus the root of b, that'll essentially get rid of the surds. You'll have a plus or minus 2 times the square root of ab plus b. So you'll essentially get rid of these surds. You will have this surd left, but that is alright, because most of the time you'll be dealing with a difference of two squares or conjugation. Then we have the distributive law. With the distributive law, notice I have some surds here. K times the root of a into n times the root of b plus m times the root of c. Of course, I could take this number outside and multiply it by the one inside. So I'll have k root a times, this dot means multiply, n root b. Then I'll have the plus sign, and I'll have k root a times m root c. And of course, in this situation, you're just multiplying the k and the n to give you kn, and you multiply your a and your b to give you the root of ab. Right? Plus km times the root of ac. So this is kind of how the distributive law works. So you can see I have an example here. The first example I have is 3 root 2 times 4 root 3 plus 7 root 5. And of course, I could take the 3 root 2 times 4 root 3, and that'll be 3 times 4 into the square root of 2 times 3, right? Plus 3 times 7 into the square root of 2 times 5. So the numbers inside the roots, you can multiply them. You'll end up get 12 root 6 plus 21 root 10. And guess what? I have some examples for you here. Rationalizing the denominator. Let's check example 1. Now, why do we like to rationalize? What do we mean by rationalizing the denominator? You see, I have 4 over the square root of 5. Remember, this is an irrational number, right? I don't like to have an irrational number in the denominator of a fraction. Remember, the denominator is what you're dividing by. So if you have an irrational number in the denominator, that means that you don't even know what you're dividing by, because we don't know what an irrational number is, the exact form of it. So we don't like irrational numbers in our denominator. We try to remove them anytime we get them, right? Because it's not good. Your fraction will be hopeless then. So guess what? We're going to use the equivalent fractions method. To remove this, I'm going to multiply by root 5 over root 5. Well, root 5 over root 5 is 1, right? So obviously root 5 times root 5 will be 5. And then I'll have 4 times root 5. So now I have 4 root 5 over 5, which is the same as saying 4 over 5 root 5. Now there's no more irrational number in the denominator. So we have rationalized the fraction. If we look at part B, you can see that I have 2 plus root 7 over 3 root 7. This implies that I need to get rid of this root 7. So I'll multiply by root 7 over root 7. So that way, I'll have this multiply by my root 7 over here, and then I'll have this multiply by my root 7 over here. Of course, root 7 times root 7, the roots will be gone, you'll just have 7. And of course here, root 7 times 2 is 2 root 7, and root 7 times root 7 is just 7. So now I have 2 root 7 plus 7 over 21, no longer having an irrational number in my denominator. If we look at this one now, I have 2 plus root 5 divided by 7 plus root 5. And how do I get rid of this 7 plus root 5? Is I multiply by the conjugate, which will be 7 minus root 5. So this is what we were talking about just now, and this concept comes from a difference of 2 squares, and it'll help us get rid of that root 5 there. So now I'll have 2 plus root 5 times 7 minus root 5 on top, and then 7 plus root 5 times 7 minus root 5 underneath. Whenever you have the conjugates multiplying, it's just the 2 terms squared. So this will just be 7 squared minus the square root of root 5. squared, right? Root 5 squared, I mean. This is a difference of 2 squares, right? And of course, on the top is where I did a double multiplication, double bracket multiplication. So 2 times 7 over here. And then I have root 5 times 7 over here. Then I have 2 times negative root 5 over here. And then root 5 times negative root 5 over here. So that'll give me 14 plus 5 root 5 minus 5 all over 49 minus 5, which will give us 5 root 5 plus 9 all over 44. We have rationalized the denominator. There is no more irrational surd in our denominator. It's bad manners in mathematics to have a surd in your denominator. Let's do B. Remember, I want to rationalize the denominator, so I will use the conjugate of the denominator. And yes, this and this can cancel, but I will not cancel them. I will multiply this way. And remember, we just talked about this. Whenever you're dealing with this situation, that is the root of 10 squared plus 2 times the root of 10 times root 3 plus the root of 3 squared. Thank you. Did I make any mistakes? Is that what you guys got? Can the root of 30 reduce any more than that? What are the factors of 30? I mean, 10 and 3, both are irrational. 5 and 6.
5 and 6.
Yeah, but both are irrational as well. So I guess we can't really reduce that root 30 any more than that. So that was pretty much surds. So what we're going to be looking at now are exponential equations. Finish this table and sketch the graph for me. So what is y when x is negative 3? Anybody?
0.25.
Sure, but you seem to be forgetting your laws of indices, right? I'll take 0.25. Is 0.25 you get?
I get 0.25.
I don't think so.
No, 0.25, yeah.
Yeah, but it wouldn't even be 0.25. Right? Because this, yeah, this, according to your laws of indices, means this, and which is 1 over 2 twos are 4 twos are 8. And 1 divided by 8 is not 0.25, that's 1 divided by 4. 1 divided by 8,
Isn't
125, yes, 0.125. So this could be seen as 1/8 or 0.125. When x is negative 2, what is that?
0.25.
Yeah, which is 1/4, which is 0.25. Of course, this will be a half, and
Yeah.
when x is 0, this will be 1. X to the power of 1. Well, 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3. 2 2s are 4, 2s are 8. 2s are 16. 2s are 32. Now, if we check this, we are in negative numbers there, right? So this is 0. In this way, we go into negative infinity. Notice, negative infinity really just means 1 over a big number because it's a power. So all of the answers will be positive. If you really check it, right? When x is negative 2, a quarter might be about here. When x is negative 3, 1/8 might be about here, right? When x is negative 1, we go into a half. When x is 0, we go into 1. And I know it not seeming like 1 on my graph, right? When x is 1, we go into 2. When x is 2, we go into 4. When x is 3, we go into 8. When x is 4, we go into 16. When x is 5, we go into 32. So notice that as x tends towards negative infinity, right? As x tends towards negative infinity, y tends towards 0. Yeah, we're getting closer and closer to 0, but we're not actually getting to 0. What do we call that? An asymptote, right? And of course, 6, 2 2s are 4, 2s are 8, 2s are 16. And then this next one will be 64, which will be really high up. So this is what we call an exponential increase. If you ever hear that word before, exponential increase. You could see that it is increasing rapidly. And you could see that the further down the negative side we go, the further towards 0 we will get, but we will never actually reach 0. Because remember, a fraction over a very big number is just something that's very close to 0. And so there will not be anything. Y is equal to 0 is a horizontal asymptote, right? Notice the domain of this graph is x is an element of integers. X could be positive, x could be negative, x could be anything, plus or minus, right? So x is an element of integers, is the domain here, but the range is y will be greater than 0, not even equal to 0, right? Y is anything greater than 0. Y less than 0 does not exist. So this is the graph of the exponent. In the next class, we'll be talking about the logarithmic graph, which is actually the inverse of that. Consider 2 to the x is equal to 64. We had to solve for x here, right? Solve for x, right? If we could express (64) as an index with base 2. This implies that 2 to the x is equal to 2 2 2s are 4, 2s are 8, 2s are 16, 2s are 32, 2s are 64. That is 2 to the power of 6. So once we could express these two numbers with the same base, then obviously x will have to be equal to 6. If I have a to the x is equal to a to the m, then x is equal to m. Number 2, if I have 9 to the x is equal to 243. This could be seen as, remember your laws of indices, 9 is really 3 squared. So that is 3 squared to the x is equal to, and 243 could be seen as 3 to the power of 5. Remember your laws of indices, right? And if you don't, we will just review them in the next class. But you can multiply these two indices here. So that means 3 to the 2x will be 3 to the 5. Therefore, 2x is equal to 5. X is equal to 5 on 2. Number 3. Imagine I have a situation like this, where I have 2 multiplied by 8 to the x plus 2. Yep, you're seeing that right? And that is equal to 16 to the x plus 1. Sure, I could take this 8 here and I could say, well, you know, that is 2 into, that 8 could be seen as 2 2s are 4, 2s are 8. That is 2 cubed, all to the power of x plus 2. Right, and that is equal to this 16 here could be seen as 2 2s are 4, 2s are 8, 2s are 16. That could be seen as 2 to the 4th, all to the power of x plus 1. So this could be seen here now as 2 multiplied by 2. And remember this 3 multiplying by that. So that is 3 times x plus 2. And that is equal to 2. And this 4 multiplying by that. So that's 4 times x plus 1. And so that'll be 2 to the power of 3x plus 6 is equal to 2 to the power of 4x plus 4. Remember, this is 2 to the 1. When you're multiplying the same base, you add the indices. So this will give us 2 to the power of 3x plus 6 plus 1. And I'm sure you all could see where this is going from here. So this will give us 2 to the power of 3x plus 7 is equal to 2 to the power of 4x plus 4. Therefore, 3x plus 7 is equal to 4x plus 4. I could throw the 3x on that side and I could throw the 4 on this side, so I'll get 4x minus 3x here, which will give me 7 minus 4 here, and so I'll get x is equal to 3. Number 4. I have 8 to the power of x plus 8 to the power of x plus 1, and that is equal to 576. And of course we have to solve for x. Notice that when you have two numbers with the same base multiplied, that means you could add the indices, right? So this could be 8 to the x plus 8 to the 1 multiplied by 8 to the x. And 500, well, we're going to deal with the 576 just now. Notice they both have 8 to the x in common. So I could actually factorize 8 to the x into 1 plus 8. 8 to the x times 1 is 8 to the x. 8 to the x times 8 is this. And that is my 576. And of course, I could see here that 9 times 8 to the x is 576. So 8 to the x will be 576 divided by 9. 8 to the x will be 64. Well, look how that worked out. Because 8 to the x is equal to 8 squared. 8 8s are 64. Therefore, x is 2. One more example, and then I'll just give you all 2 or 3 questions to go home with, and that'll be it for today. Last example. I have 2 to the power of 2x plus 1. And that is going to be equal to 5 times 2 to the x plus 12. We had to solve for x. So obviously this here means 2 to the 2x multiplied by 2 to the 1. And I could take this and bring it across on this side, and it'll become minus 2 to the x times 5, and that'll be equal to 12. Well, you know that this here, right, like is 2 to the 1 times 2 to the x squared, and you can see how I kind of pulling the 2 to the x out, right, minus 2 to the x times 5 is equal to 12. So this is how we have to be able to manipulate this thing now. And this one is a very interesting one indeed. Because if you check it, right, and I'll just change this. Let me just change this here. Sorry about this. But instead of 2 to the x times 5, I'll put 5 times 2 to the x. If you check it, right, I could throw across the 12 as well. Right? Yes, I could factorize, but if I factorize 2 to the x out of here, sorry, that's not 2x. It's 2 to the x. If I was to factorize 2 to the x out of here, I would get 2 to the x times 2 times 2 to the x, right, minus 5. I still have 2 to the x inside of here. So, you know, it doesn't really help me. If I throw the 12 across, things might start to look familiar. Because I'll end up with 2 times 2 to the x squared minus 5 times 2 to the x minus 12 is equal to 0. 2 to the x equals y. So now I have 2y squared minus 5y minus 12 is equal to 0. And we could factorize this. And for the sake of factorizing it, the factors will end up being 2y plus 3 and y minus 4. Therefore, 2y plus 3 is equal to 0. And so y will be negative 3 on 2, or y minus 4 is equal to 0. Y will be positive 4. Remember this. Y is 2x. Therefore, 2 to the power of x is equal to negative 3 on 2, or 2 to the power of x is equal to positive 4. The graph of 2 to the x is greater than 0. Therefore, 2 to the x equals negative 3 on 4 does not exist. Hence, I now have 2 to the x is equal to 4. Therefore, 2 to the x is 2 squared. Hence, x equals